Okay, are you able to see my screen?
Yes, sir.
Okay, yeah, fine. Okay. Uh, yeah, so good evening. Today I am going to discuss the week 5 assignment of the previous year. So we have completed till now till week 4. So today is week 5. So I will solve the assignment of week 5 of the previous year. Okay, you just go through it, and he will understand most of the topics clearly. Okay, I will discuss everything clearly. If you have any doubt in any point of time, then you can unmute you and speak. I will reply. Okay.
Okay, sir. No issue.
Okay, fine. Yeah, so today I am going to discuss the BJT in CE mode, that is the common emitter configuration, CE configuration. Okay, so BJT in common emitter configuration. So in common emitter configuration, how the BJT works as an amplifier, that I will discuss. This is the amplifier. Just a second. Yeah. So how it used as an amplifier, that I will discuss. Okay. Yeah. So I want to actually draw the BJT, simple BJT. So this is a simple BJT in which this is the emitter terminal, this is the base terminal, and this is the collector terminal. So this is basically a NPN configuration, which is this collector is N, this base is P, and this emitter is N. So this is a NPN configuration. So you must have learned from the lecture of Professor N.B. Patil that this BJT can be written, can be reconfigured using this hybrid pi model. So what is the hybrid pi model? According to the hybrid pi model, this BJT can be redrawn by this thing. So this terminal is the base terminal. Just a second. Okay. So this terminal is base terminal, and this terminal is the emitter terminal, and this terminal is the collector terminal. Okay, so between base and emitter there is a resistance which is known as R pi, across which if potential drop is V pi, so here from the collector to emitter there should be a current source which is nothing but Gm into V pi. That means the transconductance multiplied with the voltage that turns into the current. So this is, there is a current source, and this is the whole picture or whole scenario. So this is the base and this is the collector, there is the emitter, and between base and emitter there is a resistor which is denoted as R pi, and across which we have a drop of V pi. Okay, so the current flowing through this is denoted as IB, that is a small signal current, small signal base current. Here it is denoted as IE, which is the emitter current, and from here the current flowing through this denoted as IC, which is the small signal collector current. Okay, so this is a basic configuration of this NPN transistor. Okay, so this is known as the hybrid pi model. Why pi? Because it is similar, uh, similar like pi, right? In the pi we have one like this structure. Okay, so this structure is this emitter, and here we have two lines. So these two lines. So this is known as the hybrid pi model. Okay, you understood. So now the if you consider few other factors also in this model, so there may be a capacitor which is connected between the base and emitter, which is known as C pi. There is some capacitor that is connected to between the base and collector, which is known as the C mu, and there is some output resistance which is denoted as R0. Okay, So actually we want to simplify this model so that it remains simple, and whatever we are simplifying, that assumption is also valid in our cases. Why? Because in this actually, this c pi and c mu, basically it is very large amount. This is known as a parasitic capacitance. This is very large amount, very large. So whatever resistance is offered, the resistance or impedance it offers, which is denoted as 1 by j omega c, right? So if c pi is very large, if this is very large, so that means this becomes the 0. That means this we can ignore this capacitance, or this maybe it's a c pi, or it may be a, c mu. So it is not considered in our case. So we may simplify this model to a simple version. And also this r naught is the output resistance. So this output resistance is basically too high in the in this configuration. So basically we ignore this r naught, we ignore this c mu, and we ignore this c pi, and we calculate rest of the things considering a simple model, so that the calculation become easier, and also what approximation we have to, that also becomes valid, and the answer, or to find any particular value in the problem, that is close to the actual design actually. Okay. So today I will start one by one. So assume that NPN BJT has VBE 0.7 volt in the active and the saturation mode, and VCE, that is the saturation region, that the voltage is 0.2 volt. Similarly, for the PNP BJTs, if we consider the PNP BJTs, then the VEB is 0.7 volt, and in the active saturation mode, and VEC, that saturation, that is equal to zero point 0.2 volt in the saturation region. So we normally take this VT, which is known as the thermal voltage, thermal equivalent voltage, that is 26 millivolt at room temperature. And beta is very large unless specified. That means if beta is not mentioned, then we can consider beta equal to infinity. And as I have already discussed, that if beta is equal to infinity, then alpha can be written as beta divided by beta plus 1, right? So if we divide beta in the numerator and the denominator side, so we get, sorry, so this turns to 1, this turns to 1 plus 1 by beta. And if we put beta equal to infinity in this equation, so alpha becomes 1 divided by 1 plus 1 by infinity, that turns into 0, so it will become 1. So we know that the IC is basically alpha into IE, that means alpha is equal to 1, so that means IC equal to I, right? In other way we can say that IE is basically IC plus IB, and IC equal to IE, that implies that IB is equal to 0. So in one word we can say, if beta equal to infinity, or beta is if there is nothing mentioned in case of beta, and so we can assume that the beta to be very large, that means beta equal to infinity, and that denotes that IB equal to 0, and whatever the current in the collector flowing, that much current will be flowing through the emitter, IC equal to I. Okay. So now in the first question it is discussed, for the common emitter amplifier shown in the figure, assume that the BJT is operating in the active mode. Okay. So what is the IC? So this is some things. This is the actually the common emitter amplifier configuration. So a supply voltage VCC is applied, and there is some resistor, and basically this VCC, that amount, that is uh, potentially divided into this terminal, because there is one resistor and there is another resistor. So it divided in some part, and that much voltage is appeared to the base terminal, and that base terminal actually applied to the base, so that this transistor can be worked in the active region. So according to that, we can calculate the IB, that is the current through the base, and from there we can easily calculate the IC, which is nothing but IC equal to beta IB, that is beta times IB, and we know beta, if it is given in the question, here it is given in the question 120, so we can calculate the beta, and from there we can calculate the amount of VC, that is the collector emitter voltage, and from there we can verify the yes, if VC is greater than 0.2 volt, then we can verify yes, whatever we have assumed that the BJT is working in the active region, then that thing valid. Okay, and if VC is less than 0.2 volt, that means that the VC is in the saturation region. Then what we do, if after applying these equations, if we find out like VC is less than 0.2 volt, then we strict VC to 0.2 volt, and then using the back calculation we find out what is the value of IC, and from there we can find out the value of the IB. So this is the basic things. Okay, yeah. So now here it is asking that for this common emitter amplifier configuration, assume that the BJT is operating in the active mode, what is IC? So at first we will do the DC analysis of the circuit. DC analysis. DC analysis. Okay. So here remember one thing, here we are using one capacitor which is CB. So whatever voltage we are applying, this value, this voltage, that is the AC input voltage or AC input value, that is easily transferred to the base terminal of the this base terminal of the transistor. Okay, so by using the DC, we actually bias the transistor. That means the we bias the transistor, that whether the transistor will be in the active region or saturation region or cutoff region. And if it acts as in a active region, suppose we bias the transistor in such a way that in this configuration the transistor acts in a active region, right? And then whatever we are giving the input, suppose this Vs is 1 millivolt, so this 1 millivolt signal will amplify it using this BJT, and in the output VO we get a amplified version of the same signal. If we give 1 millivolt input sinusoid signal, then we will get 1 volt, that is a very high amount, that amplified signal. So it amplifies the AC signal. Okay, so the important of the biasing is, with this biasing we bias the transistor in in certain region according to our application. If we want it to be as a switch, so we can bias it in such a way that it can act as in saturation region, or it can act in a cutoff region. So if it acts in a saturation region, then it can be used as a on switch, and if it is act in a cutoff region, then it can be worked as off switch. Okay, so basically using this DC bias, at first we bias the transistor in our desired configuration or desired mode, maybe in active, maybe it saturation, or maybe it cutoff, and then we apply a input signal, that is input AC signal. Maybe it is a very small signal, that is, this is known as a small signal because we do the small signal analysis of the signal, right? So this AC input signal may be a 1 millivolt sinusoid, that is peak to peak 1 and minus 1, right? 1 to 1 to minus 1 millivolt peak to peak sinusoid signal. Then after amplifying this thing, it appears in a output voltage which may be very large, like 1 volt or so. Okay, yeah. So at first we will do the DC analysis. So whatever in this configuration we can see, if we apply any DC voltage, so this 12 volt, so there is a 12 volt DC, right? So I will draw the DC equivalent circuit. DC equivalent circuit. So DC equivalent circuit, how it is forming? So there is 12 volt, and from this 12 volt we have one R1, and then we again have some R2, and R2 is connected to ground. Okay, so and here we have, so no DC voltage will go this side. Why? Because this is a capacitor, and we know that the impedance of the capacitor is 1 divided by j omega c. Now at DC, frequency is equal to 0, right? Frequency 0 refers that omega is equal to 0. So if omega equal to 0, that means that z turns to infinity. That is, it offers an infinite resistance to the DC signal. That means it behaves as an open circuit in a DC signal. Open circuit, okay, in the DC signal. So whatever DC we are applying, so it should not go to the input side of the, that is the this in the VS side. So here no DC signal will flow, right? Because it is blocking the DC. So often it is known as a DC blocking capacitor. This is also DC blocking capacitor, and this is also the DC blocking capacitor, and this is known as a AC coupling capacitor. That means it couples the AC. It means it can pass the AC. So this DC, the DC value, it cannot flow through the capacitor. Okay, so the DC equivalent circuit becomes, so this is the RC and this is the RE, right? RE. So here no DC can be flow through this, here no DC can be flow through this, so we consider only this part of the circuit. Okay, yeah, okay, so we consider only this part of the circuit. So this is the 12 volt, that is the known as VCC, and here is R1, which is nothing but this is 20k, this is 15k, this is the value of RC, and this is the RE, which is 3.3k. Okay, so now it is given in the question that this common emitter amplifier, assume that this BJT is operating in the active mode. So we have to find out what is the value of IC. Okay, so we will look through this terminal, we will look from through this terminal, and we will see that what equivalent voltage and resistance is applied from this side, and we will simplify this circuit to that equivalent resistance and the voltage, right? So we are considering this whole thing as a load. Okay, we are considering this whole thing as a load, and we are looking from this side. Okay, so if we looking from this side and apply the Thevenin theorem, so that means there is some 12 volt source, and there is R1 and there is R2, these two things, which is 15k and which is 20k. So if we look from this terminal, so whatever in this, I am just ignoring this thing. If we look in this side, so here the equivalent voltage, so VTH, that will be this 12 volt, which is 12 into this resistance, which is 15, divided by 15 plus 20, that means 35. So this much voltage is applied in this terminal, which is the Thevenin equivalent voltage. So this is 3, this is 7, that is 36.7. Okay, so just 1 second, I'm using the calculator. So 36 divided by 7, which is 5.143 volt. So this much voltage is applied in this terminal. Okay, so in this terminal, so equivalently, if we find out what is the value of the Thevenin resistance, then how can we decide? So to find out the Thevenin resistance, we short this terminal, this voltage source. So assume this is short now. So now whatever the current is flowing, it is divided into two part and it goes to ground. Here also it is ground, here also it is ground, because it is short, right? So it's short means it is ground. So this 15k and this 20k comes into parallel, right? So this Thevenin equivalent resistance is 15 parallel 20, right? So 15 into 20 divided by 35, again it's 3, it's 7, that means 60 divided by 7. So it is 60 divided by 7, which is 8.571. So 8.571, this much kilo. So we will redraw the circuit. Yeah. So we will redraw the circuit like so. This much Thevenin equivalent voltage, which is VTH, which is 5.143 volt, that is applied in this side, and there is some resistance, which is RTH, which is nothing but 8.571 kilo ohm. This is applied, and then there is some RE and there is some RC, and here it is 12 volt, right? So it is applied. So the value of RE is 3.3 kilo ohm, right? So if we consider the input KVL or input side means base emitter side, base emitter terminal. If we consider this base emitter KVL equation, then we get this VTH. So if we assume that IB current is flowing through this, So we can write VTH minus IB into RTH minus, there is certain voltage drop VBE which is nothing but 0.7 volt, which is already given, minus here the current is flowing is IE in the through the emitter terminal, so IE into RE is equal to 0, right? So now we can write as 5.143 minus IB into 8.571 minus 0.7 minus, now IE, this IE can be written as IB plus IC. So it is IB plus IC is nothing but beta time IB, beta time, sorry, yeah, beta time IB. So you can write as 1 plus beta time IB if we take IB common, right? So here it can be written as 1 plus beta into IB into RE. So what is the value of RE? RE value is 3.3, 3.3 equal to 0. So we take IB in one side, we get 8.571 plus 1 plus beta. So what is the value of beta given? So beta, it is mentioned, it is 120, right? Yeah. So this will be 120 plus 1, that is 121 multiplied with 3.3. It is nothing but 5.143 minus 0.7. Okay. So IB comes as, so I am using the calculator, 5.143 minus 0.7, which is 4.443, 4.443 divided by, here now it is 8.571, 8.571 plus 121 into 3.3, so it is 407.871. Okay, yeah. So now if we divide this thing, 4.443, yeah, so it will come as 0.01089, that much milliampere, because we have considered all the resistor in kilo ohm, right? So whatever the answer that will come, that will come in the milliampere, right? Yeah. So now we got the IB, and as this as it is already mentioned in the question that the BJT is operating in the active mode. So basically the IC value will be nothing but beta time of IB. So what is the value of beta? That is 120 into 0.0189, that much milliampere. So if we multiply it with 120, we will get 1.3 milliampere. So what is the value of IC? The value of IC will be nothing but 1.3 milliampere. So here in the given answer, the answer, correct answer will be answer B, that is 1.3 milliampere. Okay, so this is the correct answer. So have you all understood this problem, or do you have any doubt?
No, sir.
Okay, fine. Yeah. So yeah. So I am moving forward to the next question. For the amplifier of question 1, what value of RC is required to obtain the value of VC equal to 5 volt? So now for the same question, what the RC value is not given, and we have to find out the value of RC, so that the VC, that means the collector emitter voltage across it, that will come as 5 volt. Okay. So now how we need to find out? So we have, now we have determined the value of the IB, which is nothing but 0.1. So this is 0.01089, that much milliampere, and IC value we have find out like 1.3 milliampere. So if we consider only this part, that is if we do the DC analysis means we consider only this part. Okay, so only this part we are considering. Okay, if we consider only this part, so now if this collector to emitter, if we apply the output, that is collected emitter KVL, then we get, here we have VCC voltage, so VCC minus, so IC is flowing through this IC, so minus ICRC minus VCE, that is this voltage VC, there is a drop, and there is another drop which is minus IE into RE, right, is equal to 0. So VCC is 12 minus IC, we have seen that 1.3, and RC we have to calculate, and here it is mentioned like VC should be 5 volt, right? So here it will be 5 minus, again it is IE, so IE is basically IE is basically IB plus IC. So IB is IC divided by beta plus IC. So if we take IC common, it will comes 1 plus beta plus 1. So IC beta plus 1 divided by beta. Okay. So minus, so it is IC into beta divided by beta plus 1 into RE. So RE will be 3.3 is equal to 0. So 12 minus 1.3 into RC minus 5 minus IC into beta means 120, beta plus 1 means 121 into 3.3. So, oh sorry, so this IC is it's already mentioned, already we have derived, it is 1.3, right, this thing, 1.3 into this. So if we consider RC, then that will come 12 minus 5 minus 1.3 into 3.3 into 120 by 121 whole divided by 1.3. So I'm calculating this thing, 12 minus 5 minus 121 into divided by 120 divided by 121 into 3.3. Okay, so it is 2.5616 divided by 1.3. So 2.2561, sorry, it will be 6565. Okay, 6516 divided by 1.3, and this is coming as 2.039, that much kilo. Okay, so the value of the RC should be close to 2 kilo ohm, so that the VC across it comes as 5 volt. So this is the answer, so it should comes as 5 volt. Okay, so do you have any question regarding this problem?
No, sir, no any.
Okay, okay. So basically, whatever we have found out, so we have done the DC analysis of the circuit. That is, we at first we have draw the equivalent DC equivalent circuit of this common emitter based configuration, and then through the input KVL we found out what is the value of IB, and then uh, using the equation IC equal to beta IB, we found out the value of the IC. Okay, and using that IC we found out the value of VC, that is what is the value of the VC that should be there. Okay, so as VC is greater than 0.2 volt, so here VC is 5 volt, so it should act in the active region. Okay, okay, okay. So in the next problem it is asked, with the RC set to the value obtained in the question 2, that is what is the value of RC, 2 kilo ohm, right, we have found out. So this is nothing but 2 kilo ohm. So now what is the value of GM? So we basically know that the IC can be written as IC is nothing but IS e to the power VBE divided by KT. This is the basic equation, right, how the IC is dependent on the input that is the voltage in VB, right? So we know the GM is nothing but the transconductance of the amplifier. So this is the transconductance, and this GM can be denoted as del IC divided by del VBE. So if we found out what is the voltage, del IC divided by del VB from this equation, then we can get del IC divided by del VBE is nothing but IS e to the power VBE divided by, so sorry, this is VT, or we can write KT by Q. VT is nothing but thermal equivalent voltage, which is KT by Q. Okay, so VB divided by VT into 1 by VT if we do the derivative, right? Okay, so we got this is IS e to the power VB by VT, which is nothing but the IC, right? This is the IC, so IC divided by VT. So GM is basically can be written as IC over VT, and if we found out the value, then we get this GM value is nothing but IC. So what is the value of IC? So the value of IC that we have determined, this is 1.3 milliampere. So it is 1.3 milliampere, and this VT is 26 millivolt, right? So 1.3 milliampere divided by 0.026 volt. Okay, so 1.3 divided by 0.026, which comes as a 50 millimho. Okay, because gm is basically current divided by voltage, so it has a unit of ohm inverse, or you can denote it as mho, right? So the transconductance of the amplifier that can be determined using simply derivating the del IC with respect to del VB, and we get it to be 50 millimho. So this is the thing. So here we get this thing as 50 millimho. So the correct answer will be answer A. So this was a easy question. So now I'll move forward to find out the rest of the values. So with RC set to the value obtained in question 2, what is the value of R pi, right? So this R pi, so to find out the value of the R pi, you should know the equivalent model, which is so this is the base terminal, and from here we have some resistance, which is nothing but R pi, and along with that a voltage drop of V pi happens, right? So this is the terminal, which is the emitter terminal, and here we have one current source, which is nothing but GM V pi, and this is the collector terminal. So the GM can be written in terms of the DC voltage. So DC from the DC bias condition, we find out that GM can be written as IC divided by VT, and in the this is called as the DC analysis, using the DC analysis, and from the AC analysis we found out that the beta can be written as GM into R pi. So GM can be written as beta divided by R pi. So we know that what is, so to find out the R pi, from here we have to divide the GM, sorry, the beta GM. So we know the beta value, that is 120 divided by this GM value what we have calculated already. So we have a GM value of 50 millimho, so that will be 50 millimho, and now we get it is 2.4 kilo ohm. This is milli, right? So it turns into kilo. So 2 kilo ohm should be the value of the R pi. So the correct answer will be 2.4. So remember one thing, from the DC analysis you have already seen in the lecture. In the lecture also, sir has described that how the GM is connected in case of DC analysis, and also in case of the AC or the small signal analysis. So you should have remembered that this GM will can be determined by IC divided by VT, and similar thing that from the small signal model you can get beta divided by r pi. The GM can be get by beta divided by r pi. Okay, so thus these two equations are related, and from there you can find out the value of the GM, or if you know the value of GM you can find out the value of r pi if beta is already known to us. Okay, okay, so this is one thing. So from the RC's from this same question you can find out the what is the value of the r pi. Okay, okay, so moving forward to the next question, that with RC set to the value obtained in question 2, RC, what is the value of the RC? This is 2 kilo ohm, right? Yeah, RC is 2 kilo ohm. So this is 2 kilo ohm. So suppose the R2 is varied, that means R2 is not 15k. So if R2 is varied, then at what value of R2 approximately the BJT just enters saturation? So the BJT is in active region when we found out that Vc should be greater than 0.2 volt. So BJT is in saturation region if the Vc is less than 0.2 volt, right? If it is greater than equal to 0.2 volt, then it works in active region, and if it is saturation region, then Vc should be 0.2 volt. So we consider now the Vc equal to 0.2 volt, and we found out what is the value of the R2, so that this Vc becomes 0.2 volt, right? Okay, so how can we proceed? So now we know now this Vc is 0.2 volt. So if we apply the output KVL, or output KVL, that means this collector base KVL, so we get VCC minus ICRC minus VCE minus IERE equal to 0, right? So VCC is nothing but, so now this VCC is nothing but yeah, so VCC is nothing but 12 volt minus IC. IC is, this is IC, so it is RC is nothing but twice into IC minus this VC can be written as 0.2 volt minus IE. IE is nothing but IC plus IB. IB can be written as IC plus IC divided by beta into RE equal to 0. So RE equal to 0. Okay, so this is 12 minus twice IC minus 0.2 minus, if we take IC common, so it will get beta plus 1 divided by beta into RE. RE means 3.3 equal to 0. So IC we get, so here it will be 2 plus beta plus 1, that means 121 divided by 120 multiplied with 3.3 equal to 12 minus 0.2, which is nothing but 11.8. Okay, so IC is nothing but 11.8 divided by 2 plus 121 divided by 120 into 3.3, so 118 plus 2 plus Okay, I'm using the calculator. 120 divided 121 divided by 120 multiplied with 3.3. Yeah, so it will be 3.3275. So now that will comes as 20 divided by, yeah, so it will come as 2.2149 milliampere. Okay, so now we got the value of the IC. So using the back calculation, I have already told you that the BJT works in the saturation region. So using the back calculation, we find out what is the value of IC, and from there we can find out what is the value of the IB. So IB is basically IC divided by beta, that means 2.2149 divided by 120, that much milliampere. So it is 2.2149 divided by, okay, so it is coming as 0.01846 milliampere. Okay, so this is the value of the IB. Now if this is the value of the IB, so what is the value of the IE? IE is nothing but IC plus IB, which is 2.2149 plus 0.01846 milliampere. So it is nearly 2.23 milliampere. So IC is near about 2.23 milliampere. Sorry, IE. So we got the value of the IE. So we got the value of the IE, what it is flowing, and also we have got the value of the IB, what is the value of IB. Now if we apply the input KVL, then we get, using the input KVL, the VTH will be VTH. So the Thevenin equivalent voltage at this terminal, if we look from this side, the input Thevenin equivalent voltage will be 12 into R2 divided by R1 plus R2, and RTH will be R1 parallel R2, right? So R1 parallel R2 is nothing but R1 into R2 divided by R1 plus R2, and from the input KVL we get VTH minus IB into RTH minus 0.7, which is VBE, minus IE into RE, right? So IE we already got, like 2.23 milliampere into 3.3 equal to 0. So now this so IB value we also got. So now it is VTH is nothing but 12 R2 divided by R1 plus R2 minus IB into RT. So it is R1. R1 is nothing but, R1 is already given in the question, which is 20k. So it is, 20 R2 multiplied with IB. So what is the value of IB? 0.01846, that much milliampere. Okay, is equal to, so this thing is equal to 0.7 plus 2.23 into 3.3. So 2.23 into 3.3 plus 0.7. So it will come as 8.059. Okay. So now we got 12 R2 minus this 20 into this thing. Okay. So this is 0.3692 R2 is equal to this. This is R1 is nothing but 20. So 20 plus R2 multiplied with, in this side, 8.059. So it will come as 20 into 8.059. So 161.18. Okay, plus this thing, that is 8.059 R2. So if we come in this side. So this is 12 minus 0.3692 minus 8.059. This much into R2 is nothing but 161.18. Okay, so if we calculate this thing, 12 minus 0.3692 plus 8.059, so this is 3.5718. This much R2 is equal to 161 plus 0.18. Okay, so what is the value of R2? R2 is nothing but 161.18 divided by this whole thing, that is 3.5718. Okay, so this value, 161.18 divided by 3.5718. Okay, so it is coming as 45.125 kilo. So here in the answer it is given, okay, oh, so I have done one mistake, it may be 4.5125. So okay, so the correct answer will be 4.5 kilo, right? Okay, so in this question, do you have any doubt regarding anything? Okay, so basically we are doing the back calculation over here. If the BJT enters in saturation region, then we consider that in the saturation region the VCE value is nothing but 0.2 volt, and from there we streak this VCE value to 0.2 volt and we calculate the value of the IC. So whatever IC we have got, so using this equation in this output KVL, we got the value of the IC, and from that IC we got the value of the IB, and from this IB if we apply the input KVL, so we can find out that what is the value, that is this value of R2 that is required, so that this IB this input KVL satisfied, and that much R2, that denotes that this R2, this is the value of the R2 when the BJT just entered in the saturation region. So in this way you have to solve the problem. Okay, yeah. Okay, so moving forward to the next question. With RC set to the value obtained in question 2, that is 2 kilo ohm, here it is 2 kilo ohm. So suppose R2 is varied, at what value of R2 the BJT just entered in the cutoff region. So the BJT is just entering in the cutoff region. So how you can determine this thing? So basically, if the BJT is in cutoff region, that means no current is flowing, that is IB is equal to 0, and also the no current will be flowing through the emitter, that means this IE is also becomes to 0. So if IE is equal to 0, so here from here IE current is flowing through the resistor, so this IE is equal to 0, that means there is no voltage drop, so this voltage drop is equal to 0 volt. So this is basically the ground terminal now, and now the VBE, this terminal VBE, we know this VBE should be 0.7 volt at least to turn on. So this, that means that VB minus VE should be, if it is less than 0.7 volt, then it will not act, then it will not conduct, that means here it is the PN diode, right? So that means if it is less than 0.7 volt, now V is connected, the emitter terminal is connected to ground because no current I is flowing, so no voltage drop. So this ground terminal appears here, the same potential, ground potential. So VB should be less than 0.7 volt, right? So VB is equal to 0.7 volt. So now if VB is equal to 0.7 volt, then the equivalent circuit what we have found, like there is some VTH value, that is the Thevenin voltage, and there is some resistance, equivalent resistance, which is the RTH resistance, and then we have this circuit, right? So whatever the circuit is there, so this is 12 volt, and this is RC, this is RE. So now this terminal is 0.7 volt, and now no IV is flowing through this, no IV is flowing through the IV is equal to 0. That means whatever VTH is applying, so this much VTH should be less than 0.7 volt, 0.7 volt VTH. Now if VTH, so what is the value of the VTH? So VTH, if we use the voltage divider here, that means if we look in through this terminal and find out the Thevenin equivalent voltage, we found out this VTH will be nothing but 12 into R2 divided by R1 plus R2. So that should be less than 0.7 volt, or that equal to 0.7 volt. So 12 R2 is equal to 0.7 into R1. R1 means 20. So into 20 plus 0.7 into R2. So it will be 11.3 R2 is equal to, so this is 14. So this is 14. So now it will come as R2 is nothing but 12 divided by 14 divided by 11.3. 14 divided by 11.3. So it will come as 1.238 kilo, right? So the value will be 1.2 kilo. So it will be 1.2 kilo ohm, so that 1.238 or 1.2 kilo ohm, so that the BJT just entered in the cutoff region. Okay, so that will be the answer. I think you all understood how I have solved this problem. The BJT is entered in the cutoff region. That means there should not be any IV flowing through this. So this IV turns out to be 0. That means there should not be any voltage drop in here, and also you have I is equal to 0, so no current is flowing through here. So this terminal, that means this terminal is ground, and now this VB, that should be at least 0.7 volt to conduct. So this terminal is 0.7, and as there is no current flowing through this, so the VTH should be equal to 0.7 volt. That means that whatever the voltage we have applied over here, that should be come in this side. So now the VTH we have found out using the Thevenin equivalent voltage, that is nothing but the voltage divider rule, 12 into R2 divided by R1 plus R2, and from there we found out the value of the R2. So at that value of the R2, the BJT will just enter in the cutoff region. Okay, so this is the answer. Okay, fine. Okay, so in the next question, with RC set to the value obtained in question 2, that is RC is nothing but 2 kilo ohm. So what is the mid-band gain of VO by VS? So what is the mid-band gain VO divided by VS? That should be that we need to find out if the RL is very large. Okay. So okay. So this, if we draw the equivalent, the AC equivalent circuit of this, that is small signal model, that is small signal model, which is known as small signal model, or AC equivalent circuit, or AC equivalent circuit. Okay. So now I want to discuss with you one thing. Uh, if we draw the equivalent, if we draw the equivalent model of this NPN transistor, considering all the thing, so this is the base terminal, this is the emitter terminal, and this is the collector terminal. So from base there is one resistance which is known as RB, that is the base resistance, and then you have one resistance which is known as R pi. All these are internal resistances, and here at R pi if there is some voltage drop of V pi, then it will appear here, which is gm V pi, and here you have one output resistance which is R naught. Okay, so if we consider all the internal parasitics or internal capacitance, then there is one capacitance C pi, and here is one capacitance which is C mu. Okay, so now what happens is, if I make one chart like using this thing, suppose there is some capacitances and there is some frequency. Okay, so what happens is, there are some external capacitances in the circuit, and also there are some internal parasitics or the internal capacitances. So internal capacitance are like C pi, C mu, whatever we have already done, right? This is the C mu, which is nothing but the capacitance between the base terminal and the collector terminal. C pi is nothing but the capacitance between the base terminal and emitter terminal. And the external capacitance means, in this diagram you can see, this is the external, these capacitances CV, CC, coupling capacitance CE. Okay, so now what happens is, if we consider the low frequency model, these external capacitances are very less. Suppose you, the all the external capacitances value is nothing but 1 microfarad, means it is in the order of in the microfarad, and the internal capacitances are in the order of 1 picofarad. Okay, so whatever is happening, so suppose, in the low frequency operation, suppose we are using 1 kiloradian per second. Okay, the omega value. So we know that the equivalent impedance is nothing but 1 divided by omega c, right? So if omega is 1 kiloradian per second and c is 1 microfarad, so this impedance comes out to be 1 kilo ohm. Similarly, for the 1 picofarad, this is 1 giga ohm, right? Yeah, and in the range of the midband means, suppose if you are considering 100 kiloradian per second, then this value comes out to be 10 ohm, near about 10 ohm, and here it will comes out to be 10 mega ohm, right? 100 times less, right? And if you consider it, it is operating in the high frequency region. High frequency region means, suppose 1 gigaradian per second, then this value can be written as 0.001 ohm, and also this thing can come as 1 kilo ohm. So whatever we generally do, uh, for the AC analysis, small signal analysis, through this band, that means the mid band and the high frequency range, this is very less amount. So we consider this as short circuit. That means for the midband analysis and the high frequency analysis, we consider the external capacitances are to be short, right? So that means we don't consider the external capacitances, the effect of external capacitances, because it's in very less, it provides very less resistance. And what happens in term, in case of internal capacitances, this 1 giga ohm and 10 mega ohm is very high. So for low frequency analysis and midband analysis, it can act as an open circuit, because it offers very high resistances. Okay, very high impedances. So that means, so in the low frequency analysis, we cannot ignore the effect of the external capacitances, that means the CV, CC and CE. And in high frequency analysis, we cannot ignore the effect of C pi and C mu. But in our cases, we can ignore the value of the C mu and also the C pi, because we are considering the midband analysis, right? So here in the question also it is given, like what is the value of the midband gain. That means the frequency is neither low neither too high, neither too low neither too high. So we ignore this C pi and C mu. And also, so that means this can be taken as a open circuit. So this is open circuit, so we are not considering this thing. This is open circuit. And similarly, in this case also, this capacitance also. So in the AC analysis, what we do, this the simple simply passes through the capacitor, so we don't consider the effect of the capacitor. We only just consider that at mid band and also in the high frequency, the capacitance can behave as a short circuit. So in the AC or small signal analysis, we consider these three things to be short circuit. Okay. So this is the thing I want to discuss. And also this RB value, that is too much too less, that is the base resistance value, so ignore this thing. And also this R naught, that depends on the early effect, so that is too high, that tends to infinity, so sometimes we don't consider the R naught. If R naught is given in the question, then we consider, otherwise we assume that R naught is very large, so it is infinity. So we just consider this model, this is base, and there we have only R pi, that is the resistances, and across that V pi voltage or potential is applied, and this V pi multiplied with Gm, the transconductance, and it flows from collector to emitter terminal, and there is some load. And R pi R naught, which is the output resistance, that is also tends to infinity, that we don't consider. Okay. So so now we have to draw the midband gain VO versus VS if RL is large. So now I am considering all these things. I am drawing the small signal equivalent model. So whatever, so when we draw the AC signal or the small signal model, it is known as small signal model, then we we prefer to do the DC ground. That means the DC is ground. So this 12 volt, we replace this thing as a ground, or the 12 volt is not there, right? So how we can draw this small signal model? So the VS is applied here. So we have VS over here, the VS. This is the thing, and the capacitance I have already discussed. This acts as a short circuit, right? So there is short, and then from here we have two part. R2 is going to ground, so this R2 is going to ground, so this terminal is ground, this is R2, and another resistance R1, it is also going to ground because we don't consider DC. So R1, this is going to ground. Okay, R2 and R1 both are going to ground, and then it then it comes to the base terminal, right? Base terminal. And what I have already discussed, between base and emitter there are some resistance, right? So which is known as R pi. So here is R pi, and across that V pi potential is generated. And then if we have any collector terminal, so the GM V pi is applied over here. Okay, so this whole thing is the equivalent model of the NPN transistor. Okay. Okay, so now what is happening, from the collector terminal, from this collector terminal we have this CC is short, right? Because the capacitor acts as a short circuit, and then we have RL and ground. So here is one RL, it goes to ground, and also from the collector terminal there is some RC and it goes to ground, right? So here is some RC and it goes to ground, RC, it goes to ground. Okay, so this is the equivalent small signal model of this diagram. Okay. Yeah, so now what is the question? The question is which RC with RC set to the value obtained, question 2, what is the midband gain VO versus VS if RL is large? So RL is very large, that means RL tends to infinity. So RL is tends to infinity, that means we don't consider this, we consider this as open circuit. So now we calculate the value of the V pi. So now here the potential is Vs, so across this node the Vs potential is applied, so we simply see from this circuit that Vs equal to V pi, right? And now as RL is very large, this GM V pi, here no current flow either in this side or this side, because if the current flows, that has to be returned back, that is not possible. So no current flows from this side or this side, right? So now what is the voltage of this VO, that is the output. So output voltage, you can see right here, it is written VO across RL. So here it is VO, right? Okay. So what is the value of the VO? So VO is nothing but this GM V pi, the direction in this side, downward side. So that is entirely flowing through the RC, right? And here it will be the potential drop will be in this side, right? Plus and minus. So VO is nothing but the minus GM V pi into RC, right? So this output voltage, and we found out like V pi is nothing but Vs. So minus GM Vs into RC. Now if we consider VO divided by Vs, it is nothing but GM into RL. Sorry, GM into RC. So GM we got the value 50 millimho, right? We have already discussed 50 millimho. We have already derived, and then RC value, it is RC value is 2 kilo ohm. So it is 2 kilo ohm. So it is 2 kilo ohm. So that means minus 100. So here the magnitude of this value VO versus Vs is 100. So remember one thing, in the common emitter configuration, whatever you have applied, this is 1 millivolt signal, that will be enlarged and it will be in the opposite phase always. Suppose this is 1 volt, this is minus 1 volt. So it will be enlarged and opposite phase. That's why what the minus sign denotes. That means the VO and Vs will be out of phase. The phase shift between this will be 180 degree, and the magnitude will be 100 times. That means whatever you have applied the input signal, the output signal would be 100 times of that signal, and that will be 180 degree phase shifted. So 100 will be the answer, the midband gain, VO versus Vs. Okay, do you have any question? Okay, okay, I am moving forward to the next question. So, with RC set to the value obtained in question 2, what is the midband gain VO versus VS if RL is 2 kilo ohm? So, RS is 2 kilo ohm. So, if we draw I am drawing again the small signal model, it is VS. So, there is R1, and then again there will be R2. Okay, so that will be GM V pi, and here we have only R pi and V pi, and here you have RC, and also you have RL, and here you have VO. Okay, and this thing to be ground. Okay, so we know this V pi is nothing but equal to Vs from the input circuit, and from the output circuit VO is nothing but minus GM V pi RC parallel RL. Okay, so minus GM into Vs into RC parallel RL. Now VOVS is nothing but minus GM RC parallel RL. So minus GM means this is 50 millimho, and it is 2 kilo ohm parallel 2 kilo ohm, because RL is now 2 kilo ohm, right? And RC already we have determined in question 2. So 2 parallel 2, that means minus 50 millimho. It will be half of that is 1 kilo ohm, which is nothing but minus 50. So what is the magnitude is? Magnitude is nothing but 50. Okay, so this is the midband gain VO versus VS we have calculated. This is nothing but minus 50, right? So this GM V pi is flowing across this RC and RL, and RC and RL is in parallel, right? So RC parallel RL. That's why we have written RC parallel RL. So using this thing, we got the value of the VO versus VS, which is nothing but minus 50. Okay. Okay. Yeah. So next question. With RC set to the value obtained in question 2, what is the output resistance of the amplifier seen from RL? So what should be the output resistance? Okay. So for each of the question, you have to draw the equivalent small signal model, and then you have to calculate small signal model. So here you have Vs, and then you have R1 parallel of R2, and then you have R pi, across which V pi voltage drop appears, right? Okay, and then you have this current source which is GM V pi, and across that you have RC parallel of RL, right? RC, I am drawing these two things separately, RC, and this is RL, and now you have this thing as VO. Okay, yeah. So so what is asked in the question, what is the output resistance of the amplifier as seen from RL? So we should look from the RL terminal. So what we do, we generally remove the RL terminal and put a voltage like VTH source, and suppose the VTH source is suppose ITH current is flowing from the VTH source, and then we found out through the equation what is the value of VTH plus I divided by ITH, that will be the Thevenin equivalent model RTH, or nothing but the output resistance of the amplifier. So if we put a VTH source and suppose ITH current is flowing through this, so now what is happening? So to find out this, so we put this Vs is equal to 0. So if Vs is equal to 0, so there will be no V pi, so V pi will be equal to 0 again, and as GM V pi, this current source, that will become 0. This current source 0, that means this current is current source nothing but the open circuited. So if we flow, the ITH current is flowing through this terminal, so this entire ITH will flow from this RC. So, and this VTH will be nothing but ITH into RC. So VTH by ITH, which is the equivalent resistance R output, or you can say it R Thevenin, that is nothing but the value of the RC, and RC value we have already found out, that is 2 kilo ohm. So this output resistance or RTH resistance, that should be equal to 2 kilo ohm. So that will be the answer. So you understood, right? Vs we need to be 0 if we found out the Thevenin equivalent resistance, or what is the equivalent resistance from there. If we apply VTH and ITH considering other to be 0, so Vs is equal to 0. That means the V pi which is applied through this, that will also be equal to 0. So GM V pi will be 0. That means that will be the open circuit. So this current source will not be there. So whatever the current flowing from this terminal, that will flow through this circuit, and if we apply this using the KVL, so VTH is nothing but ITH times RC. Now we have to find out the VTH divided by ITH to find out the equivalent output resistance. So VTH by ITH, which is the RTH or R out, that is equal to nothing but RC, and RC value is 2 kilo, so it is 2 kilo. So the correct answer is B. Okay, yeah. Okay, so the next question, with RC set to the value obtained, question 2, same thing. What is the input resistance of the amplifier as seen from Vs? Okay, so now here it is Vs, here we have R1, R2, R pi. Okay, in the small signal model you understood, right, why we are putting this emitter terminal to ground. Wait one second. Yeah, so all these things are ground. Okay, all these things are ground. Why? These things are ground, you understood, right? R1 and R2 is directly connected to the ground. R1 is connected to ground because we are considering the AC or small signal analysis, so DC should be 0. R2 is also connected to the ground, and in the emitter terminal, this is the base terminal, this is the collector terminal, this is the emitter terminal, and the emitter terminal, it is for the AC small signal analysis, this will go from this side, CE, so it will not see any RE resistance, it will act as a short circuit, right, CE. So we don't consider RE over here, so RE will not be there, so it will directly connected to ground. So that's why we draw this diagram like this. Okay, small signal model. But if there is no CE, then there will be some RE equivalent resistance RD over there, and then we have to find out the value using this KCL KVL like that. Okay, as it is connected to ground, so it is too much easy to calculate all the things. Okay, so here also it is R pi, it is V pi. Similarly, these all things are ground, and emitter is also connected to ground. This is the base terminal, and here also you have nothing but GM V pi, and you have R naught. R naught is infinity basically, so you don't consider R naught, rather you consider RC and parallel with RL. Okay, and here you have plus minus, which is VO. Now what is happening? Okay, so you have to find out the input resistance of the amplifier seen from Vs. So you remove this Vs source, and you put a VTH and RTH over there, VTH over there, and suppose ITH current is flowing through this. So this entire current will divide into three parts in this part, and these three things are in parallel. So VTH by ITH is nothing but the parallel combination of R1 parallel R2 parallel R pi. Okay, so this is the answer. So RTH is nothing but 1 by R1 plus 1 by R2 plus 1 by R pi. This whole thing's inverse, right? So 1 divided by 20 plus 1 divided by 15 plus 1 divided by R pi. What is the value of R pi we have obtained? 1 second. R pi we have calculated, right? Uh, yeah, R pi is 2.4 kilo ohm. Yeah, so 2.4 kilo ohm. So yeah, so it will be 1.2.4 kilo ohm. Okay, so now 1 divided by 20, which is 1 divided by 20, 0.05, 0.05 plus 1 divided by 15, 0.067, 0.067, and then you have 1 divided by 2.4, 0.4167, 0.4167. So, and all these things inverse. So if we add these things, you get 0.67. So, yeah. So it is 0.5337 inverse, right? So you will get 1 divided by this, so 1.874, this much kilo ohm. So so that is close to the 1.9 kilo ohm. So 1.874, which is nothing but 1.9 kilo ohm. So this is the thing, RTH value is nothing but this. Okay, yeah. So I move forward to the next question. The T model is an alternative small signal model of a BJT. So in case of BJT, we have two model. One is hybrid pi model and another is the T model. So it is shown in the figure along with hybrid pi model. The parameters of the hybrid pi model of a specific BJT operating under some specific bias condition are given. R pi is twice kilo ohm, GM is 50 millimoh. So what is the value of alpha? Okay. So here we can see whatever the current flowing through the collector, that is nothing but alpha E. It is mentioned alpha E, right? And it is the collector current IC, right? And here in this case, whatever the IC current is flowing, that is nothing but GMVB. So IC in hybrid pi model, it is GMVB. This is the hybrid pi model, hybrid pi. And in case of this T model, this is nothing but alpha into IE. Okay, so now GM This VB is nothing but the IB multiplied with R pi. So IB into R pi, and this alpha, this I is nothing but IB plus IC. So IB plus IC means beta into IB. So it is written as 1 plus beta into IB. So alpha into 1 plus beta divided by IB. Okay. So this IB and IB cancels out. So GM R pi is nothing but alpha 1 plus beta. And you know, always know, GM is nothing but beta, equal GM alpha is nothing but beta. So this is the thing. So alpha is nothing but beta divided by 1 plus beta. Okay. So now, okay, the okay, all the parameters are given in terms of GM into GM R pi. So GM R pi divided by 1 plus GM R pi. So GM R pi is twice into 50 divided by 1 plus twice into 50. That means 100 divided by 101. So it is 100 divided by 101. It is 0.990. So the correct answer will be answer C, 0.990. So we can use this hybrid pi model in AC signal analysis, or else we can use this T model also in the AC signal analysis. So both are connected like this. Okay. Yeah. Okay. So the next question, it is asked, in the T model of the same model, what is the value of RE? So this is the thing which is RE, this thing. So how this is connected to this? Okay. So there is a base terminal, this is a B, and there is a emitter terminal E. So here whatever the voltage drop is happening across the RE, that is nothing but VBE. So small bb is nothing but equal to IE into RE in case of T model, right? And in case of pi model, hybrid pi model, this VBE, this is nothing but IB into R pi, IB into R pi. So this IE into RE, IE means beta times 1 into IB into RE is equal to IB into R pi. Okay, so IB cancels out. Now this RE is nothing but R pi divided by beta plus 1. So R pi, what is the value of R pi given? R pi is 2 kilo ohm. So 2 kilo ohm divided by 100 plus 1, that is 101. So 2 divided by 101, which is 0 0.1, sorry, 0.0198 kilo ohm. If we multiply 1000, so it is nothing but 19.8 ohm. So this will be the correct answer. Okay. Yeah. So do you have any question till now?
No, sir. I don't know anything.
Okay. Okay. Now here is one thing. The push-pull amplifier configuration is shown in figure. The transistor beta values are 150 and 80 for Q1 and Q2 respectively. So Q1 is 150 and Q2 is 80. Okay. So with Vi equal to 2 volt, what is I1? With Vi is 2 volt, so Vi is 2 volt is applied. What is I1? So note that only one of the transistor can conduct. Okay. So this is a hint. So basically you have to verify that whether this hint is correct or not. Okay. So what is the thing? So here you have this uh, NPN NPN transistor, and also you have PNP transistor over here. Okay. So this is the base terminal, this is the emitter terminal, and this is the collector terminal. Similarly here it is the emitter terminal, it is the base terminal, it is the collector terminal over here. Now what is happening? So here, if q1 is on, suppose q1 is on, so this thing, that is the VBE should be greater than 0.7 volt, right, to turn on this BJT, otherwise it will be in saturation region. Sorry, otherwise it is in cutoff region. So VB should be greater than 0.7 volt. That means this B, consider this is as P node and this is its Q node. Okay, so P terminal is nothing but B terminal. So VP, you can say P terminal, this is Q terminal. This should be greater than 0.7 volt. Okay, and to turn on the Q2, you should have VEB greater than equal to 0.7 volt. This is for Q1 and this is for Q2, right? So VEB means this terminal. So here the VQP should be greater than equal to 0.7 volt, right? Emitter terminal is this thing for this, because it is PNP and this was NPN, right? So PNP, so Q terminal, which should be greater than P terminal, that is 0.7 volt. So to turn the Q1 on, you need VPQ greater than 0.7 volt, and to turn the Q2 on, you have to VQP should be greater than equal to 0.7 volt. But this cannot happen simultaneously, right? Either VP should be greater than VQ or VQ should be greater than VP. So these two things cannot happen simultaneously. Okay, simultaneously. So considering only one on at a time, you have to solve this question. So now you have input voltage 2 volt, right? 2 volt. So for this question, when you have the input voltage 2 volt, so that means this 2 volt is applying over here. So obviously it will be greater than this VB 0.7 volt. So you just assume this Q1 is only on, so and Q2 is off, right? Q2, why Q2 is off? Because here this 2 volt is applying in this base terminal, and here you don't know what is the output. So if it only turns on, then it will be ground, right? It will be ground connected if Q2 is only on, and this is 2 volt, so which is not satisfying this thing, that this VQP greater than 0.7 volt. So you consider, so we have decided like Q1 should be on and Q2 should be off. So if we redraw the circuit considering only Q1 on and Q2 off, because Vi is positive, right? 2 volt, yeah. So here you have RB, here you have VK 5K, this is Vi, and the current flowing through this is I1. Okay, now it is flowing through Q1. So this is I2 and this is 5 volt. Okay, okay. So now what is happening? So yeah, okay, so I1 current is flowing through this, and here it is I2, right? Yeah, and here you have the load resistance RL equal to twice K. Now you apply the input KVL. This is VBE. Input KVL. If you apply the input KVL, you get VI minus I1 into RB. I1 is flowing through RB minus VBE minus I2 into RL is equal to 0, right? Okay, so Vi is nothing but 2 volt minus I1 into 5 minus 0.7 minus I2 into 2. I2 means this is I2 into 2 equal to 0. Now I2 is nothing but the current flowing through the emitter terminal, right? It is nothing but emitter terminal, which is nothing but collector plus base. Again, this is beta time base into plus IB. So IB, if we take common, beta plus 1, right? So this I2 can be written as 2 minus I1 into 5 minus 0.7 minus beta plus 1 into I1 into 2 is equal to 0, right? So if we take I2 common, which implies 5 plus this 2 into beta plus 1. Beta is nothing but, here in the question it is given 150, right? For Q1 it is 150. So 151. 150 plus 1, right? 151. It is 2 minus 0.7, which is 1.3, right? Okay. So I1 5 plus 300 to 1.3, and I1 will be 1.3 divided by 307, that much milliampere. Okay. So 1.3 divided by 307, 0.00423, this much milliampere, or you can write 4.23 microampere. So this is the value of the I1. Okay. So here, what is the value of the I1? So the I1 value will be 4.2 microampere. Okay. Okay. Uh, so the next question. Okay. In the next question, it is asked, for this push-pull amplifier with Vi equal to 2 volt, what is the value of the I2? So the same question, what is the value of I2? So you have already calculated the value of I1. So I1 is nothing but 4.23 microampere, and I2 is the current flowing through the emitter terminal, which is beta plus 1 into IB. IB is I1, right? So beta plus 1 into I1. So beta is 150 for this first transistor into I1. I1 is what? I1 is 4.23 microampere. So 151 into 4.23 microampere. So 151 into 4.23. So it will be 638.73 microampere, or 0.638 milliampere near about. So it will be 0.64 milliampere. It is the correct answer. Okay. Do you have any question? Okay. So for the next question, okay, question number 15. So for the push-pull amplifier of question 13, if Vi is minus 2.5 volt, what is the value of the I1? Okay. So now what is happening? Minus 2.5 volt is applying in this terminal, which is Vi. So here now, so it is a negative. So suppose this thing Q1 is, Q2 is on. So that means this is minus and this has to be positive, and Q1 is off. So if it is off, then this is at the zero terminal, zero ground, and this is minus 2.5. That means it is greater than VEB, right? So Q2 on, that we assumed is right. Okay. But if we assume that this is on and this is off, then what happens? It is minus 2.5, so this is minus 2.5, and this is off, so this is connected to ground only, so here it will be 0. So this VB is not greater than 0.7 volt. So whatever we have assumed that Q1 is on, that is not valid. So this will not be valid. So this thing is valid, that is Q2 on and Q1 is off, right? Q2 on, Q1 off. Okay. So how to solve this? So we will draw again the circuit. This is 5K, this is RB, this is VI, and this is I1. This is minus 5 volt. This is RL and this is 2K. And here the current I2 is flowing through this. Okay. So now if we apply the KVL, this is the emitter terminal, this is the base terminal, this is the collector terminal, right? So this thing is VEB, which is nothing but 0.7 volt. Okay. Yeah. So now if we apply the input KVL, VI minus I1 RB minus, sorry, it will be plus VEB, because the plus is in this direction, right? But here the plus is in the opposite direction, right? Here also it's opposite direction. So minus I2 RL is equal to 0. Very good. So now what is happening? VI minus 5 into I1. VI is minus 2.5, right? So minus 2.5 minus 5 I1 plus 0.7 minus I2. I2 is nothing but, by similar manner, beta plus 1 into I1 into 2 equal to 0. Now what is the value of beta of transistor 2? In the question it is given 80, right? 80. So minus 2.5 minus 5I1 plus 0.7 minus 81 into 2 into I1. So 162 plus 5, this much I1 is minus 2.5 plus 0.7, which is minus 1.8, or I1 is nothing but minus 1.8 divided by 167. So this is minus 1.8 divided by 167, sorry, minus 1.8 divided 167, so which is this much milliampere, which is minus 0.010778 milliampere, or in micro you can write 10.78 microampere, minus 10.78 microampere. So it is close to minus 11 microampere. Okay. So answer D will be the correct answer. Okay. Okay. And so the next problem, for the same push-pull configuration, VI is the same thing, that is minus 2.5 volt. So what is the value of the I2? So similarly, whatever I1 you have found out lastly, which is 10.78 microampere, which is 10.78 microampere. So IT will be nothing but beta plus 1 into I1. Beta is 80, so 80 plus 1 into 10.78 microampere. So 81 into 10.78. Okay. So 81 into 10.78. So it is 873.18 microampere. So it will be near about 0.873 milliampere. 0.873 milliampere. So it will be actually the minus sign, because the direction of the current will be in the opposite direction. So it will be minus 0.87, right? So this will be the answer. Okay. Okay. So do you have any question till now? Yeah, please. Hello. Hello. Yeah, you can unmute and speak. Hello. Okay. Hello. 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 Okay. Actually, if you don't have any question, then